Hello and welcome to this video on the center of mass. In this video, I'm just going to quickly talk through what the center of mass is, what it really represents for an object, and then we'll look at how we can find it. So, what is it? Well, to answer that, let's think all the way back to when you were learning about projectile motion. I'm sure that in there somewhere somebody made a claim that basically if you throw something, it's going to undergo projectile motion, and what that means is it will make, supposedly, a parabolic trajectory. So let's put that to the test. Say I'm going to throw a rectangular object, and what I'm going to do is pick one of the corners and trace out how that thing actually moves. So if I do that, then the path is obviously not parabolic. There's some element that looks parabolic to it, but there's a whole lot of looping going around in this motion. So, okay, maybe that's particular to the corners. Maybe the other points do well. So let's pick one at random, somewhere sort of in the middle, but not quite, of this block. In that case, we've improved perhaps a little bit. There's not as much looping going on, but it's still making this overall sort of flowery shape not a simple parabola. So was that a complete lie that you were fed? Fortunately, it's not a complete lie. It's just a simplification. There is one special point that actually does undergo parabolic motion, and that special point is the center of mass of this box. And since this box is, you can assume, nice, symmetric, uniform density rectangle, then basically where the center of mass is the same as just being the actual center of that object. And so if you track that point, what you do find is a nice parabolic motion. All right, so the center of mass is the thing that executes that parabolic motion that was claimed for projectile motion. So the center of mass describes the overall simplified translational motion of an object. It's the point that actually moves according to all this kinematic stuff that you learn. So it's quite important because then that is giving you the overall behavior of the system. More often than not, you don't care about the fact that the rectangle tumbles. You want to know how far it moves to the right, and that is obtained by doing calculations that assume this parabolic trajectory. And it's the center of mass then that you're really talking about. So how do you find the center of mass of an object? Well, it's got to do with how the mass is distributed. And in fact, the location of the center of mass is just sort of a mass-weighted average position. What I mean by that is these formulae here. So the location along the x-axis of the center of mass is given by basically every little piece of mass times that particular coordinate location in the x-axis, add those up, and then divide by the total mass. And you can do the same thing in the y direction to find the y coordinate of the center of mass. And I could talk about this equation all day. The best way to understand what's going on here is to see an example. So let's go ahead and do one example. So suppose I've got a 10 kilogram mass, a 2 kilogram mass, and a 3 kilogram mass, as shown there. Just oriented so that the 10 kilogram mass is 3 meters off to the left of the 2 kilogram mass, and similarly the 3 kilogram mass is 2 meters below that 2 kilogram mass. So the question is, where is the center of mass of this system? And even without doing this, if we just think about the concept of mass-weighted average position, we should be able to develop an intuition. What we mean by mass-weighted average is that we care more about wherever most of the mass is actually located. So the center of mass should be closer to that 10 kilograms. So that's one prediction we can make. And then, of course, as we go through our calculation, we'll have to bear that in mind in order to check whether we've gotten this thing in any sense right. So in doing this, we need to pick some coordinate origin for our system. So if we're going to do that, then we'll go ahead and pick this 2 kilogram mass, because we're free to choose anything, and we'd like to pick one that makes this crazy summation easy to evaluate. So as we go through, it should become apparent why I've chosen that 2 kilogram mass as my origin. So we need to know the x-coordinate of the center of mass. Well, that is going to be, I've got 10 kilograms situated at -3 meters, because it's 3 meters to the left of my 2 kilogram mass. my 2 kilogram mass is situated at x equals 0, and similarly, the 3 kilogram mass is situated at x equals 0. The total mass is 15. And you can see, hopefully, why I've chosen the 2 kilogram mass to be the origin, because by doing so, I've knocked out 2 of the masses from this x calculation. So it made my life much easier. I'm just looking at negative 30 on 15, which is, of course, negative 2 meters. I'm just carrying over my units. So as far as the x-coordinate is concerned, we're done. It's 2 meters to the left of this 2 kilogram mass, and then at some y-coordinate, that's where I'll find the center of mass. So to complete the problem, let's go ahead and grab the y-coordinate of the center of mass. So again, what's going on? Well, I have a 10 kilogram mass, but that's actually sitting at y equals 0. Then I've got a 2 kilogram mass sitting at y equals 0. And then I've got a 3 kilogram mass sitting at negative 2 meters. That's 2 meters. And so I can compute what that gives me, again, on the total mass, which is 15. And that gives me simply a negative 6 on 15, which I can rewrite negative 2 fifths. Okay, it's just factoring out common factor of 3. So I'm slightly to the left of the 2 kilogram mass. I'm 2 meters to the left of the 2 kilogram mass, and slightly below, so 2/5 of a meter, 0.4 meters down. So this thing, center of mass, is somewhere maybe here-ish. Okay. It's a little bit rough, but it's somewhere in there, and that's consistent with what we said. It's closer to the 10. It's been pulled down because we have this extra mass down here, and it's been pulled a little bit over to this side because we have 2 of those 2 masses dragging it out of the 10 kilograms. Okay, so that's how we find the center of mass. And basically, the key there is that the center of mass is talking about sort of the average location of all the mass in some object. And that center of mass is the single point of the object that undergoes the simplest translational motion. It's also the point that you consider as basically representing that object. So if you're not interested in the tumbling, you're not interested in the shape, you just want to consider where is that object, then you talk about the center of mass. So for instance, if you're calculating the gravity from this object, you just need to know how far are you from the center of mass of that object. In order to check your understanding of the concept of center of mass, here's some food for thought. This is a very common little trick that you can do to amuse your friends. It looks very magical, but now you should be able to understand this. So think about it a little bit. Where is the center of mass of that sculpture? If you can answer that, you understand both the concept of center of mass and how this trick works.